It's very grateful to be here, as always. So I'm John Carpenter. I'm an independent research scientist and consultant right now. And my talk is going to focus a bit more on the implementation side of decision making rather than the prediction side, using results chains with Bayesian networks. And it's an exploratory presentation. I'm going to focus on environmental conservation and ecology kinds of management decisions with hypothetical examples, but I hope this is broadly applicable to other fields. So this is just a generic decision analysis framework that's pretty much matches most types of formal decision analysis processes. And so at the top we have problem formulation. This is the qualitative phase where you determine your objectives, determine your performance measures for your objectives, identify your alternatives, and formulate the problem for consequence modeling. And the consequence model is the next phase. That could be qualitative and or quantitative. And that would be something like developing a Bayesian network to predict the impacts of alternatives on objectives. And we also have a value model that has to be constructed. And it could be a monetary value model or non-monetary value model, depending on the decision type. And that could also be qualitative and quantitative. And so a value model would be something like examining the utility functions for different attributes for your objectives, looking at trade-offs, things like how much money would I be willing to spend to restore X amount of acres of seagrass. That's a values-based trade-off. And you bring these two types of models together to make a prediction and a recommendation of the optimal decision. And luckily with Bayesian networks, like most Bayesian network software, we have the ability to not only include chance to things like a traditional Bayesian network, but to build influence diagrams of decision and utility nodes so we can integrate those consequence and value models. And so then after the prediction and recommendation, the decision is selected by the decision makers. That can include a no action or a status quo alternative. And then you have the implementation phase where the decision is actually implemented. So in environmental management, something that's very, very popular and that comes up a lot and is implemented a lot is adaptive management. And this provides a framework for the implementation phase. It kind of brings the science into decision making where you're testing and adjusting management decisions, especially complex environmental management ones. And you improve your decision over time and you respond to changes such as correcting courses when you see things going wrong. It also has a prompt formulation and a generic set of steps, which includes setting goals for the decision, implementing the actions, monitoring the results, and revising the approach. You should just call it the learning by doing cycle. So this is relevant for decisions that you can make where you can do repeated decisions. So it's not relevant for every type of environmental management decision. So there's three main phases for environmental management, and I've taken this is for the Everglades Restoration, this framework for adaptive management. And as the first one is the formulation phase on the far right over there. And then the next phase is design and construction of the decision. And then the final one is operations and management of the decision that's being implemented. And so formulation will integrate existing theory, data, and experience. So what's the knowledge about what could happen with this decision? And this integrated understanding is often embodied in models, quantitative models. And models make predictions about the effects of policies. And experimentation, when that's implemented, can be active or passive. So active experimentation would be designing like a scientific experiment where you're comparing different policies or comparing different aspects of the environment and what could happen. And constant is when you implement the decision and just monitor it as it goes and correct course. It's not an active like scientific experiment. So the modeling step for adaptive management provides a setting and a focal point for discussions about the knowledge base and the assumptions. It also allows us to formulate alternative hypotheses about the implementation. And we try to use this step to exclude policies that are unlikely to be effective, get rid of the things that are pretty much dominated by better alternatives. We use it to identify what the key uncertainties or data gaps are, and design the monitoring and adjust management actions to close those data gaps. And competing models are often developed and used to compare against new data from learning. And so I found a cool example of literature for kind of a meta Bayesian network model for adaptive management modeling. And so this hypothetical example might be for like centering a harvest target for like a fishery species, like a recreational fishery species for a fishing season. And so on the left we have our decision node, on the right harvest target, and two possible decisions. We could either set the harvest target low or we could set it high. And this influences the fish population size over a certain time period and whether it's decreasing, stable, or increasing. And so decreasing would be the thing you want to avoid, and increasing would be the best possible outcome. And then we also have a node representing the different competing models of the probabilities of giving like a model averaging. And so each model, model 1 and model 2, a priori are not known to be better than the others, so we put 50-50. And so let's say we implement an expected utility from this network. There's a value scale in that utility node, and it calculates what the probability and the value scale of the expected utility in BayesiaLab. And so our expected utility is 48 for the low harvest target and 61 for the high harvest target. And so that 61 would be the preferred recommended decision with this model. So let's say we implement the high harvest target and we observe what we didn't expect to see, which the fish population size is decreasing at the end of the season, fishing season. But this also updates our model predictions. And we can see that model 2 has a 89% probability now of being accurate, more accurate than model 1, which has 11% probability now. And so we could take this for the next season and use these as our model weights for making the next decision. And now the expected utility is 68 for low and 53 for high. And so we implement low this time, and we observe the fish population size is stable, and our model 2 weight increases to 98%. So we're almost certain model 2 is a better model to use than model 1. And so there's, as far as like causal Bayesian networks or structural causal models, there's a really cool Nyberg et al. Nyberg and colleagues paper, a classic one from 2006, on using Bayesian networks and adaptive management. And the steps are very common sense and really kind of cool. So step 1, you develop your Bayesian network, kind of like what we were talking about earlier. Step 2, you use the Bayesian network to develop your adaptive management experiment. Step 3, you monitor the results from the experiment. Step 4, you update your Bayesian network with probabilities as well as the structure, what you observe and what you learn. And so this one's more tactile with causal understanding. And in step 5, you repredict with your updated learning and new Bayesian network structure, and then you implement with the next decision with the new predictions, like we were showing before. So in practice, adaptive management is widely touted. You often hear it in panels and discussions about decisions and things, about its importance and its usefulness, but it's not used as often, I think, as it's recommended. And I think the reason for that would be it's kind of difficult to do in environmental management. And it takes a prolonged period of dedicated funding, dedicated resources, setting it up with all the different expertise, as well as maintaining and monitoring the decisions. It's not something that's available for every type of decision. And so adaptive code management kind of evolved in response to this, and this is more looking at it as a group thing, NGOs, industry, government kind of coming together to implemented an adaptive management process for environmental management. And you can find some great literature about harvest decisions and wetland restoration and forestry successes, especially with some of the hunting and fishing decision made. So results chains are a type of conceptual model. They're pretty much a graph or a DAG that link interventions to impacts with intermediaries in a causal chain. They're often used in adaptive management internationally for planning and implementing. You set up the result chain to evaluate progress from your initial intervention to your ultimate outcomes or objectives, and it's a nice way to make your beliefs and assumptions about the decision problem and implementation explicit. So a little bit about the history. It was first announced in a white paper by an NGO, Foundation of Success. Prior to that, it was in use over a previous decade for environmental management. It was built from theory of change tools before conservation groups started using it. And now it's used for training and for conservation standards by the International Conservation Measures Partnership. And so this is the basic result chain structure. So you have on the left, you have your inputs such as resources, funding, effort, things that go into determining what type of decision you can make. And so in decision analysis, the inputs would be like the decision context, like what are the alternatives available. And then we have our strategy, that those are our actions, candidate actions to be taken, which leads to an output, initial results of actions taken, which leads to different levels of outcomes, intermediate results, and then those lead to our ultimate target. And so we can use these intermediate results, these outcomes over here, to represent the key uncertainties or what we have to learn about within the Bayesian network for evaluating the success of a decision. So here's a case study I wanted to show really quickly of tigers and their ungulate prey in Laos, where they built a really cool results chain for protecting tigers from poaching. And so this is just a piece of it. And our initial decision on our strategy has to deal with law enforcement on the far right over here, and that leads to an increased government capacity for enforcing hunting. And so these yellow things are different interventions along the way of these different outcomes for protecting tigers in Laos that they implemented. And then on the far, over here on the far left, we have our threat reduction in purple and our ultimate objectives in green. And there's a lot of criminology in this. It's kind of interesting, you know, preventing poaching, building capacity, things like that. So I'm going to do a hypothetical case study with a Bayesian network for a hydrological optimization problem. So this stylized example, we just want to look at the swamp, forest area, mixed use, land use, environmental area that we want to move water into and out of different sections with culverts and pumping structures. And we want to maintain or optimize the water delivery for preventing severe wildfires, as well as for keeping the peat soils hydrated for forests and things. We also want to restore the forests with removals of invasives and planting. And the ultimate goal is optimization for preventing flooding, boosting ecological use, and having better wildfire regimes. And over here, this is just a picture of the Great Dismal Swamp. This is based on that or anything, but you can kind of see the water control structures of the different sections and things, and it's the difficulty, the complexity of this type of problem. So I kind of, my personal preference when I have a really complicated problem before jumping into trying to do a tag of everything is to do a logic model where I kind of have, I guess these could be viewed as objects, where I kind of group different factors together into different categories and things. And so in the gray, we have the different interventions, water structure placement, structure operation, tree removal, invasive species control, tree planting. And then this green over here represents the system. Within there, you have the hydrological system, the soil characteristics, the forest structure, and different concerns under those. The yellow at the top are the modifiers of external factors forcing functions, different terms for that. And these are things that are outside of our intervention but could influence the success. And so that could be things like evapotranspiration could be a significant source of water output, rainfall and storms, groundwater levels, as well as climate change and temperature. And then we have our outcomes over here related to wildfire, intensity, burn area, and related to our ultimate impacts in certain with ecology, flooding, carbon retention, etc. And so from this, I created, once again, this hypothetical, a complex Bayesian network, complex on purpose, for the purpose of this example. And within this network, BayesiaLab allows us to identify causal pathways within a consequence network. So when you have a complex network like this, like between any two nodes, BayesiaLab will tell you all the causal pathways as well as each one individually. And so if we take one of the water control structures, which is on the left, and we want to look at one water control structure interventions on the left, and want to look at its relationship to an intervention node, we do the influence paths to target in BayesiaLab, and it immediately tells us what are the causal pathways, so we don't have to go through and determine it ourselves between these two. And although this looks pretty complex, it really is just repeating down the depth of the model, different submodels for different regions and stuff like that. So let's hone in on one of the submodels here. So we have a control structure intervention with the blue node and the tree removal with the blue node also. And we have our chance nodes related to things like water output and retention, moisture, peat, forest composition, fire size. And we have our yellow external nodes, storm events and rainfalls. And then we have our green impacts of flooding, CO2 emissions, suppression costs for fires, and runoff events. And so let's look at the causal pathways between the control structures and the runoff events. So runoff events would happen after a wildfire. You have a dry peat that burns and hardens, and then everything, when there's a rain event, everything runs off into the nearby streams and can cause acute effects on like fish species. So here are our causal pathways between the control structures and the runoff events in dark gold and blues. BayesiaLab identifies 6 total pathways, and let's hone in on one of them initially. And so we could take this immediately from our consequence model and create a result chain, from these causal pathways that are identified, or at least a starting point for a result chain. And so on the left, we have our structure operations, move to water output from the system, to water retention, to peat moisture, to fire size, to peat burning, to runoff events. And so this is a result chain with all 6 causal pathways, individual pathways integrated. And so this adds in a few nodes, such as the forest composition node. And we can add modifiers to this to examine what could facilitate or hinder the progress along this results chain from our control structures to our runoff events. In this case, we added rainfall and a drought occurrence related to rainfall. And we could add in expertise nodes like we saw in the initial example to represent different types of modeling that go into determining our physical probability tables. We have one for novel ensemble for fire size and one for expert opinion and runoff events. And then we determine for each node, we can just have 2 states. We want to target certain areas, and so we determine the targets as well as when their time period of occurrences. For example, with water input, we could make a statement about cubic feet per second of water delivery targeted over a certain time period, X number of years. And then from this, we develop our Bayesian network and incorporate the probabilities from the information that we have available. And just like in our first example, we can run through different scenarios and examine where different interventions should occur along the result chain to help facilitate things, and plan for contingencies with it. So from the result chain literature, I made a quick little workflow for identifying result chains with Bayesian networks. So step 1 is identify the initial DAG for the problem. what is the causal structural model, add intermediate nodes as needed within the result chain, such as the causal flow model, and ask things like what additional outcomes are necessary when moving from left to right, and what needs to happen to see this outcome from right to left. And this advice could be important not only for result chain, but also in developing a predictive model to kind of make it useful for decision making. You often get questions about how do I know which nodes I should add in between this and this, and this might be a good way of doing that for the result chain for sure. So capture externalities along the chain, such as forcing functions, model expertise ensembles, additional interventions on intermediate and final impacts, and then determine target states, set goals, establish monitoring indicators for your node states, and incorporate probabilities such as data, model, and experts that iterate with the criteria for a good result chain that's established in the literature. So result chains are very simple, but they're informative about decision implementation. They can be used for one-off or repeat decision problems. Only the latter can be used with adaptive management. Their adaptability and ease of use make them attractive candidates for both analysts and decision makers. And Bayesian networks are easily adaptable to result chains. And incorporating probabilities within result chains allows additional thought about potential for achieving outcomes when implementing decisions. Okay, thank you guys.
Here's the microphone.